Okay, so picking up with part 2 of the Advanced and Applied Linear Algebra Practice Final Exam, we're given A equals 5002, E equals 0110. Define A, epsilon equals A plus epsilon E. Part A, find exact eigenvalues of A of epsilon. So this is eigenvalue perturbation theory. So we solve this determinant, A of epsilon minus lambda I equals 0, setting that up, setting it equal to 0. When we expand here, we get x squared minus 7 lambda plus 10 minus epsilon squared equals 0. And then performing the computation here, that lambda plus minus, that's going to come out to 7 plus or minus square root of 9 plus 4 epsilon squared over 2. So lambda sub plus minus epsilon equals 7 plus or minus square root of 9 plus 4 epsilon squared divided by 2. Part B, expand the eigenvalues to second order in epsilon, so second order expansion. We're going to use square root of 9 plus 4 epsilon squared equals the following, which is going to be a square root approximately 3 times 1 plus 2 2 epsilon squared over 9, that quantity, and then that equals 3 plus 2 epsilon over 3. Therefore, we're going to get lambda plus x of epsilon is approximately going to yield 5 plus epsilon squared over 3, and lambda minus of epsilon, that's approximately 2 minus epsilon squared over 3 here and here, given in the boxed answers, just reiterating that. Part C, D and E are on the next page. Compare with first order perturbation theory. Explain why the dominant eigenvalue is stable under small perturbations. And relate the result to data analysis applications. So moving along now to C, D, and E. Okay, so first order perturbation. Here's what we're first order correction is the following. Here's U sub 1. Here's that E sub 1 transpose E sub capital E sub 1, that equals 0. And for U sub 2, and we're going to get that E sub 2 transpose E sub 2 equals 0. So the first order corrections are 0, agreeing with the expansion. For the stability, the eigenvalues remain close to 5 and 2 for small epsilon. Since the gap is 5 minus 2 equals 3, small perturbations cannot easily mix the eigenspaces strongly. And for part E, the data analysis interpretation. In PCA, a large spectral gap means the leading principal component is stable under small noise perturbations. Okay, so that's number 6. Moving along now to number 7. Okay, so number 7 here, we're given the following data points. 0, 1, 1, 2, 2, 2, 3, 5. Fit a line y equals ax plus b using least squares. So just going through A through F here. Construct the design matrix, form the normal equations, compute the least square solution, compute the residual vector, verify orthogonality of the residual to the column space, interpret the projection geometrically. So this is least squares of projection theory. Here's what we were given. So the design matrix is going to be x equals column 1, 0, 1, 2, 3, column 2, 1, 1, 1, 1. And then for our y, that's just going to be this column 1, 2, 2, 5. The normal equations, x transpose x, that's going to equal that 14, 6, 6, 4. X transpose y, that column 21, 10. So if we take this and we perform the multiplication, set up 14, 6, 6, 4, and then column AB, that's going to be set equal to column 21, 10. So solving for this, the solution comes out to A is 6/5, B is 7/10. So y hat is going to be 6/5 x plus 7/10. Residual vector, so the predicted values y hat equals 7/10, 19/10, 31/10, 43/10 for that column. And then the residual is r equals y minus y hat, column 1, 2, 2, 5, minus column 7/10, 19/10, 31/10, 43/10. So that yields this column 3/10, 1/10, negative 11/10, 7/10. And for part E, the orthogonality check. X transpose R equals row 0, 1, 2, 3, and then row 1, 1, 1, 1. And that's going to be multiplied by this column 3 tenths, 1 tenth, negative 11 tenths, 7 tenths, second equal to that 0, 0. So the residual is orthogonal to the column space of X. Part F, the geometric interpretation, the least squares projects Y onto that col X. Residual is the perpendicular error, so Y equals Y hat plus R, and Y hat is the element in col X, R perpendicular col X. So that's number 7. Moving on to number 8. Okay, so consider this Y equals XB plus epsilon plus this E, and then epsilon equals 0, covariant epsilon equals sigma squared I. So derive the least squares estimator, show that is unbiased, compute its covariance matrix, state the Gauss-Markov theorem, and prove that no other linear unbiased estimator has smaller variance. So this Gauss-Markov theorem problem, so we take what we are given, least squares estimator, we're going to minimize this norm of y minus x beta squared. Here, normal equations, x transpose x, b hat equals x transpose y. And assuming x transpose x is invertible, b hat equals x transpose x inverse x transpose y. Unbiasedness, this equation here is what we're going to use. We're going to substitute for y, and then we're going to wind up with this e beta hat here. X transpose x inverse x transpose e, x beta plus epsilon, and then just performing the operations. This is just going to come out to beta at the end. Okay. Part C, covariance. B hat equals beta plus that x transpose x inverse x transpose epsilon there. Therefore, the covariant B hat equals this following. And since the covariant epsilon is sigma squared I, we get the covariant B hat, beta hat equals sigma squared x transpose x inverse. Okay, so that is for part C. Moving along now to parts D and E. Okay, Gauss-Markov theorem. Among all linear unbiased estimators of beta, the least squares estimator has minimum variance. It is the blue, best linear unbiased estimator. And then our proof sketch. Okay, well, our unbiasedness requires Cx equals I. So write C equals x transpose x inverse x transpose plus d, where dx equals 0, then that covariant there, that equals sigma squared c transpose. So we substitute, we wind up with c transpose equals x transpose x inverse plus d inverse. And since d transpose is, plus d transpose, and since d transpose is positive semi-definite, we get the following. So thus the least squares has minimum variance in that situation. Okay, and let's see, moving along to number 9. We're given this A, we want to compute A transpose A, find all singular values, find right singular vectors, find left singular vectors, construct a complete SVD, interpret the action of A geometrically. So singular value decomposition, A transpose A, set it up, we're going to get 25, 0, 0, 25 for the rows respectively. For B, the singular values, the eigenvalues A transpose A are 25 and 25, therefore sigma sub 1 equals sigma sub 2 equals 5. The right singular vectors, setting this up, v sub 1, 1, 0, v sub 2, 0, 1. Left singular vectors, For U sub I, A V sub I over sigma sub I. For V sub 1 equals Z sub 1, A V sub 1 equals 340 column, and thus U sub 1 is B 1/5 340. For V sub 2 equals Z sub 2, A V sub 2 005 column, thus V sub 2, U sub 2 is 001 column. And a third orthonormal vector perpendicular to both is U sub 3 equals this column negative 4/5 3/5 0. Okay, complete SVD, setting this up for you. This sigma 500,500 and V equals 1001. And our A value here is going to be U sigma V transpose. So that's U sigma, V transpose. Sorry about that. And for geometric interpretation, the matrix maps the unit circle in R2 to a circle of radius 5 embedded in a two-dimensional subspace of R3. Both singular values are equal, so there is no preferred stretching direction. Okay, so that's number 9, and then moving along to number 10. Number 10, we consider A is 600,030,001, A, B, C, D, E. Find the best rank 1 approximation. Find the approximation error in the spectral norm. Find the approximation error in the Frobenius norm. Explain why the approximation is optimal, and discuss implications for data compression. So this is an Eckart-Young approximation theorem. We take our A, and we could say that the best rank 1 approximation for this, the singular values are 6, 3, and 1. Best rank 1 approximation keeps only the largest singular value. So that is going to just be this matrix here. 6, the rest are zeros for the entries. For part B, our spectral norm error, that's just going to come out to 3. For Frobenius norm error, that's just going to come out to square root of 10. Optimality by the Eckart-Young theorem, truncating the SVD, gives the best rank K approximation in both spectral and Frobenius norms. And for the data compression, keeping only the largest singular values preserves dominant structure while discarding low energy directions. Okay, so that's all for part 2. Next is part 3. Thank you.